Okay, let me get back to where we were at sort of last time, and let's sort of get back into the world of development length. So last time we were discussing the issue or the concept of development length, which, by the way, if you didn't get a set of handouts, they're right here. The idea behind development length is that when we do all of these calculations and we just say, oh, well, what's the force in the rebar? Oh, it's just the area times Fy. Simple. Well, you have to ensure that there is an appropriate bond between the rebar and the concrete in order to develop that full capacity. Bless you. All right. So what we're going to do now is learn how to compute what that length is. Okay. So as we said, rebar develops its strength through the fact that it has ribs on it. Those ribs grip with the concrete. More grip equals more strength. Okay. Now, when you look at a concrete element that has failed or has suffered a bond failure, it tends to occur in kind of like a cylindrical fashion. The cracks, you can almost like draw a circle right around the rebar, and you can see that's where the cracks occur. They look something about like this. This observation, I sort of wanted to bring that back into the fold because we're going to see a dimension and a parameter here in a minute that's going to relate to this very type of failure. It's a CB distance that we're going to see in a little bit, and it's going to be a function of these types of covers that you see here. Excuse me. All right. So again, the idea is, remember again, here's my concrete beam. This is the cantilever. The beam, the top of the beam is in tension, so we put the bars on the top of the beam, again, as opposed to the bottom. Again, going back to my original example, party deck, dance floor, rebar on the bottom, no time to whip, let alone nay-nay. So the idea is we put the bars on the top, but if we don't embed those bars into the adjacent column, well, I mean, what's going to happen? It's just going to fall off. So those bars have to go back into that column or into that adjacent element a certain amount to develop that capacity. That's what we're going to try and compute is L sub D. Now, is the formula messy? Yes, the formula is messy. But it is probably one of the most plug-and-chug expressions we really will deal with. I mean, a lot of this stuff we've already seen. I mean, Fy, F sub C prime, we've got dB values. Really the only thing we need to handle is this big fraction right here. A number of those adjustment factors are really functions of just looking up values based on the conditions you're looking at. And then there's that C sub B distance and that KTR. We'll take one step at a time. Excuse me. All right. So let's start off with those psi factors. The psi factors are pretty straightforward. It's all about looking at the location of the bars. We call it psi sub t because it's related to bars on the top. It's a top bar factor if you ever are in the workplace. It's called that as well. The idea is that you go look at all the test data on concrete beams and what have you, and you'll find that the bars on the top they don't bend or bond as well as the bars on the bottom. So if you've got more than 12 inches of concrete below, we take our development length and we increase it. If any of these factors are larger than 1, that tends to be the worst case scenario because you're saying, well, you need more embedment to develop the strength of that concrete. So, or develop the strength of that bar, sorry. So if you have top bars, you're essentially looking at a psi sub t of 1.3. Okay, and again, that just comes from test data and analysis and what have you. If you're looking at any other case, we just take psi to be 1. So it's pretty simple, pretty straightforward. Now the psi sub E factor, that's your bar coating factor, and it tends to really relate to epoxy-coated bars. If you've ever seen epoxy-coated bars, they're slicker than regular bare steel. Slicker bars indicate, weaker grip. So you need more embedment in order to develop the capacity of those bars. Now there's, it's a trade-off. You get better corrosion protection with an epoxy-coated bar than you do a bare steel bar. But, just depends on the scenario you're looking at. If you've got epoxy-coated bars, your psi factor is going to be larger than 1. If you have an uncoated bar, your epoxy value is going, or your epoxy coating value is going to be equal to 1. So anytime you're dealing with epoxy coated bars, your psi value is greater than 1. Now, your psi value is 1.2 in most cases, but if you've got epoxy coated bars and they're spaced really closely together, then there's not a whole lot of concrete to grip those bars, so that psi value gets even larger. So if you've got epoxy coated bars with really narrow spacing or really small cover distances, as you see here, we take psi to be 1.5. Otherwise, we'll take it to be 1.2. Okay? Does that make sense? Pretty straightforward stuff, I think. Yes? You're talking about galvanization. You're exactly right. And galvanization is a potential coating solution that doesn't involve coating it, and you get sort of that same grip. Galvanization of bars can be a little more expensive. So again, it's a trade-off. It just depends on the scenario that you're looking at. So, yeah. But you're exactly right. If you dipped bars and didn't epoxy coat them, you could get the same benefit without having to use a larger psi value. You're exactly right. All right. Yes, sir? What was that? Very good question. Very good question. No, it was. That was a good question. It was. Mark it down. Mark it down. All right. Last one is the reinforcement size factor. And the idea is this, is that you can achieve the same area of steel requirement with a bunch of really small bars or a few really big bars. You get the same area, but the difference is you have a change in surface area. Okay? Now the idea is if you've got smaller bars, you need a lot more of them, so there's a lot more surface area for the concrete to grip. So the long and short of it is, if you have a bunch of really small bars that you're using to achieve your capacity, you actually get a benefit on your development length. Your psi value gets smaller than 1. Again, if your psi value goes up, that's sort of a worst case scenario. You need more development length to generate that capacity. If psi gets smaller than 1, it's like, hey, we're getting a benefit for something. This is a benefit. So if you're dealing with smaller bars, like number 6s and smallers, or number 6s and smaller, but you can use a psi value of 0.8 for your size factor. Otherwise, it's your default value of psi of 1. Sound good? All right. Now, this ratio here that's on the bottom, that denominator that we saw, this CB plus KTR over DB, okay? This sort of takes into account the effects of bar spacing and cover, okay? Now, let's start off with CB, okay? So I have here this reinforced concrete beam, and I've got 3 different distances indicated. I've got CB as being from the center of the bar to the edge, from the center of the bar to the other edge, or halfway over to the next bar. That CB distance is trying to account for that cylindrical failure surface that we were talking about before. Remember that? How we said that if you look at a bond failure, it tends to be cylindrical around a given bar. And basically what the spec is doing is it's defining that cylindrical failure surface as, you know, the closest distance to the next available discontinuity, either, you know, the edge here, or halfway over to the next bar. So that's what CB is taking into account. Now, just on a word of notation, in steel design, probably in about a week or so, we're going to see a CB in there, and it is going to be way different. It's not even going to be close. It's going to be a completely different factor. So just point of, you know, caution for later. All right, sound good? So that's what CB is taking into account. Now, just a heads up, this entire ratio that we're going to see here, it is limited to 2.5, okay? So when you calculate it, if you got 3.86, cap it off at 2.5, okay? Now, that KTR is what we call a transverse reinforcement index, and the idea is that, you know, that cylindrical failure surface, you know, that we were talking about a moment ago? Well, if that cylindrical failure surface is being reinforced transversely, if it's being confined in some fashion, maybe by, well, I don't know, shear stirrups. Because isn't that what a shear stirrup would do? It would wrap around those bars and confine that a little bit. If you want to account for that, you can get a little bit of benefit, okay? So a transverse reinforcement index, you calculate that to be 40 times the area of transverse reinforcement, which is basically just the shear stirrups, the area of your shear stirrups. S, which is your center-to-center spacing of transverse reinforcement, which is basically just your stirrup spacing. And then N, which is the largest number of tensile bars in a given layer. So if I was looking at this would be an N equals 3, because I've got 3 bars in a layer. Like if I had 3 and then 3 and then 3 and then 3, just N equals 3. Make sense? Yes? Yes, that's it. Yeah, no, that was a simple one. Yeah, CB is just taking this as the smallest of those distances. Basically as, from the center of a bar to an edge, or from the center of a bar halfway over to the next bar. So, there's technically 3 different options. Go from here to here, here to here, or here to here. Exactly right. All right, sound good? All right, and here's your KTR value. Okay, now a couple little caveats on the side. And this again just comes from test data and just empirical analysis. Whenever you compute development length, keep a watchful eye on these two. Whatever you compute, it's got to be less than or equal to 1.7. So if you've got, like epoxy-coated bars and they're way on the top, that value might get pretty large. You cap that off at 1.7. Now this one's a nifty one. You are allowed to reduce your development length based on the difference between the area of steel required and what you actually picked. Now what I mean by that is you all have done beam designs in this class, and you'll go through and select the area of reinforcement, and the area of reinforcement might come out to be something like 5.94 square inches, right? So then you pick 6 number 9s that has an area of steel of 6 square inches. So there's a difference between what was actually required in that beam for the purposes of design and what we actually picked. You can take the ratio of those two and actually bump down your development length a little bit based on that ratio. Does that make sense? It's not very complicated. The big thing is just making sure you understand what's the difference between the required area of steel and what's actually there. Again, the required area of steel is what you would get on like step 8 of your design. AS required equals 5.46, and then you pick 6 number 9s or what have you. All right, make sense? All right, so let's look at an example. So here's our beam. This is a pretty straightforward beam, and I want to determine the development length for these bars, these 3 number 8 uncoated bars, okay? So we'll say we're going to do it for 2 different cases. We're going to start off looking at KTR is equal to 0, and then we're actually going to compute KTR. I want to try and keep it simple. Okay, now we got normal weight concrete of 3 KSI, so our lambda value is 1. We've got FY of 60 KSI, and let's take a little bit of time and make sure we understand what's going on this beam. Okay, so we've got a rectangular beam. We've got number 3 stirrups at 8 inches, right? So let's see. We've got our cover distances down here, both horizontally and vertically. We've got our depths and what have you. So this should be a fairly straightforward calc. It's all about going through your notes and making sure that you can interpret what these individual parameters are going to be for your given beam. Okay? Does that make sense? All right. This should be a pretty straightforward problem. All right, so let's see what happens. Yes. It depends on the type of stirrups that you're using. It depends on the type of the size of the bars that you're using. It also depends, keep in mind, on your environment. It's a different scenario, for beams inside of a building than it is, say, piers on a bridge in Miami where you're exposed to saltwater conditions and those covers have to change quite a bit. or beams in you know, a corrosive environment. So my answer to you is that it depends on your cover requirements and what's actually there. You know, for typical scenarios, you're right that there are probably, you know, some typical standard values that you're always going to see. But, you know, it's engineering. There's always something complicated, you know.
I guess the same could be said for DB2. Usually it's about 3.
You are right. Most of what we've done for our beam design problems is we've said, you know, the difference between D, you know, and H for our purposes has always been 3 inches. So you're exactly right. Make sense? Sound good? All right. Excuse me. So, okay. So everybody okay with the problem? All right. So make sure you've got your lecture notes on you. Does anybody not have them? The slides. Okay. They're in your truck. Well, here. Just give it back to me when you're done. In his truck. In his truck. What's that? Been a long morning. You weren't in steel design, though. The steel design folks just got out of a 2-hour exam. What's that? Did y'all have an exam yesterday too as well? Ah. I mean, the big thing with hydraulics is just don't lose your head. Don't lose your head. Do you like that one? Okay. All right. So let's look at 15A. Let's start listing a couple things. So all right, you all have the dimensions in front of you, so I'm not going to, you know, completely repeat everything, but a couple things I want to write out. All right. So we've got FC prime is 3 KSI. We've got lambda is 1. And we've got Fy is 60 KSI. Okay? Now, we've got number 8 bars. So tell me, what is the diameter of a number 8 bar? 1 inch. Remember rebar, from number 3 to number 8, you always take that number divided by 8, and that's your bar diameter. So like a number 5 would be 5/8. A number 7 would be 7/8. A number 8 would be 8/8 or an inch. 8/8. I can't get that out easily. Okay. All right. Now, let's take a look at our adjustment factors. So we'll say adjustment factors. And we'll take them one at a time. So let's look at psi t. So psi t, that's your top bar location factor. That takes into account whether or not there's 12 inches of fresh concrete below the bars. Do we have that for this beam? No. So what is psi sub t for this beam? 1. So what I'm going to do is I'm going to say psi sub t is 1.0, and I'm going to say bottom bars. Okay? Now, what is psi sub e for this beam going to be? 1. Why? They're not coded. Exactly. So 1.0 and then uncoded bars. All right? Now, what about psi sub s? Psi sub s is the size factor. What is psi sub s going to be? 1, because they are bigger than number 6s, right? So we'll say 1.0, and we'll say that is because they are number 8 bars. Okay. Now, everybody got this? Now let's just see if we can observe, take a look at this beam and observe it and tell me what is C sub B going to be. So, let's look at our distances. Let's look at the horizontal one. How far is it from the center of a bar to the edge? 2.5. How far is it from the center of the bar to the bottom? 3. How far is it from center of a bar halfway over to the next bar? 1.5. Which one do we use? Not too bad, right? All right. Let's see. Okay. All right. So C sub B is 1.5. Okay. Excuse me. All right. So a couple things I'm going to do before we get into this. So for what we're doing right now, we're going to say KTR is 0. Later on, we're going to compute it. Okay. So a couple notes. Okay. What is psi sub t times psi sub e? What is that? 1. And that is less than or equal to 1.7, so that's okay. Okay? I know that sounds silly, but maybe on the next problem it ain't so silly. We'll see. All right? Excuse me. All right, no, I'm sorry, that's 1.5 inches, and KTR is 0 inches. Okay. So that's the first thing I wanted to compute. I also wanted to go ahead and compute that denominator. Let me go back to the slideshow. I know I keep hopping back and forth. I apologize. Here is our expression for development length. And all of this stuff here on the bottom, that ratio is limited to 1.5. So let's see what we get for, or 2.5, sorry. So let's see what we get right here for that. Again, limited to 2.5. Oh, got to do my whole full screen. Yes. Yeah, the maximum value you are allowed to use is 2.5. So if you calculate it and you get 3.86, 2.5. All right. So that ratio, it's CB plus KTR over DB is what? 1.5 plus 0 divided by 1 inch, which is 1.5, right? And that is less than or equal to 2.5. It depends on how much of a benefit you're trying to account for in your shear stirrups. Like if you've got, let's say, a really heavily shear reinforced beam, that is possible. And basically what they're saying is, sorry, that can't happen. So it's possible. It is. Like our next example, we don't hit it, but we get like 2.3. We get close. So. Sound good? All right. So we're actually ready right now to go ahead and compute our development length. So therefore, our development length is 3 over 40, and then we have lambda square root of FC prime. I can do better than that. And then we've got Fy, and we've got psi t, psi e, psi s, and then that ratio then we multiply the whole thing times dB. All right. So plug and chug. We get 3, and I'm actually just going to do it as one big fraction, everything on the top and everything on the bottom. So what's Fy? What do I put for Fy? Now, let me ask this. Do I use 60 or do I use 60,000 PSI? There you go. Because my square root of FC prime, I'm going to put in PSI get out PSI. So I need to go ahead and do that now with the FY. So on the top, we have 60,000 PSI. And then what do we have? Psi T, Psi E, Psi S, they're all ones, right? 1.0, 1.0, 1.0. And then dB, that is 1 inch. And what do we have on the bottom? We have 40. Lambda is 1. We have, the square root of what? 3,000. Remember, put in PSI, you get out PSI. So we'll... Then now we've got this ratio, the CB plus KTR over dB. What is all this stuff in the parentheses equal to? We already did that, 1.5. There you go. So 1.5. That's it, isn't it? All right, what do we have? 17.3? I got 54.8. Was that easy? That is really about how complicated development length is. We're going to do a few more examples to make sure you understand the lookups and the tables and the figures and all that, but that's it. I mean, it's a simple calc. Okay, so you all have a good weekend. I will see you all on Monday. Remember, you have a homework due. We will continue on with development length on Monday, exam review Wednesday, to have the celebration on Friday. Not on this one. It'll be on the next one. So. No, it's deflections. No. Well, you will get a homework on Monday that will have this on there, but it won't be due until next Wednesday. You got plenty of time on it. And it's 2 problems. This stuff is quick. So, all right, we'll see you next week. Y'all have a good weekend.